Hey guys, this is Rachit Jain. My effort through this set of videos is to ensure practical understanding of simple and complex concepts in the domain of statistics through college level rigorous mathematics but with school level ease. The agenda for this video would be to understand the basics of probability, its true mathematical definition, and seeking a comparison between our current existing knowledge of probability against the actual true meaning of the same. So without any further delay, let's get into it. In the previous video, we learned the concept of universal set, that's omega, and sample space S, and the subtle terminological difference between a sample and an event. This universal set omega may be finite, as in the case of a dice throw, or countably infinite, or infinitely countable, uncountable, as in the case of integer and real set respectively. Since the first two are countable in nature, that is, they can be enumerated, we use the sigma field as the power set itself. However, for the case of infinite, we switch to the Borel field of R. You can let me know through the comment section if you need a dedicated video on Borel field of R. With this clarity, we move on to defining the elephant in the room, that what is probability? A map P from S to R, that is the real set, is called probability if it satisfies the following three axioms. First, P of A is greater than or equal to 0 for any set A belonging to S. Thus, the range becomes non-negative. Second, probability over the universal set, that is the set of all outcomes, is equal to 1. However, this does not indicate that the probability lies between 0 and 1. It just says that for the universal set, the probability is 1. And thirdly, which is kind of the most important one, is that probability of union of sets AI is equal to sum of the probability of those sets itself. This is only true when the two sets AI and AJ, they are disjoint sets, like pairwise disjoint. So their intersection becomes phi. This property is called countable additive property. Here you must notice that P is defined over S, that is, probability is always defined over events and not samples. Also, the tuple omega, S, P is termed as the probability space. If you get into the concept of fields, you would understand this in much deeper sense. Now that we truly understand what probability is and that it is a function from S to R, how do these three axioms get parallel to what we knew in school? Because till now I only knew that P of A should belong to 0 and 1, right? We know that for any set A, we can write omega as A union A complement, where A and A complement are two disjoint sets. Using the second property, we know that P of omega is equals to 1. So substituting omega with A and A complement, we get that P of A union A complement is equals to 1. Since they are disjoint sets, we can write it as summation of P of A and P of A complement equals 1. So we finally get P of A complement is equals to 1 minus P of A, and that is something we learned as a property in school. From here, you can also substitute A with phi and you can get the probability of empty set to be 0. Thus, probability is non-negative. However, we are yet to show that P of omega equals 1 would imply that for any set A in S, P of A is less than or equals to 1. This would only be possible if we show that P is a monotonically non-decreasing mapping, which would imply that for any set A that is a subset of B, P of A is less than or equal to P of B. So in that case, every set we know is a subset of capital omega, the universal set, and thus we would, if we prove this to be true, we would get that the probability is always less than 1, less than equals to 1. So what we learned as a property that probability should lie between 0 and 1, let's try to prove this through mathematics. Let us assume A and B belong to S, which is the sample space, such that A is a subset of B. Here you can write B as A union B minus A, where the minus operation denotes the set subtraction. That is, any elements of A in B are removed from B. So you can visualize the various sets using this simple Venn diagram on the right. which represents A intersection B, B minus A, and A union B. So substituting B with this, we can write that probability of B is equals to probability of A plus probability of B minus A, because these two are disjoint sets, and you can see that from the figure as well. Finally, we get P of B minus A is equals to P of B minus P of A. We know that any probability is non-negative because that was our first axiom. So P of B minus A greater than or equal to 0 would imply that P of B is greater than or equals to P of A. But this is true when A is a subset of B. So this tells us that whenever A is a subset of B, P of A is less than or equals to P of B. So P is essentially a non-decreasing monotonic mapping. So let us try to visualize this using the following sets. Suppose A1, A2 are like this, and A3 is the superset of A1 and A2, and all these are a part of the universal set omega. So although we cannot compare probability of A1 with probability of A2, we can definitely say that P of A1 and P of A2 are less than equals to P of A3, and that is less than equals to P of omega, because P is a monotonically non-decreasing mapping. That is, the more like the superset we have, the higher the probability it will have as compared to the subsets. Since P of omega is equals to 1 and every set that belongs to S is basically a subset of omega, we can write that P of A is less than equals to P of omega, which is equals to 1 from the second axiom. Finally, we get P of A is less than equals to 1 for any set A belonging to S. And that is the reason we say P of A belongs to 0 and 1 for all A in set S. Hoping that we are clear on what probability is and have understood the foundation of the same, so that we never have to mug up those insights that we used to do in school, we move on to another property by the name of Bonferroni's inequality. So for a probability space omega S and P and sets A1, A2 till AN in S, we have this property to hold true. Unlike property 3, there is no condition for AIs to be pairwise disjoint in this case. Had they been pairwise disjoint, this inequality would have turned out to be the equality, and the math you can see how it works out. Since the number of events can be countably infinite, the concept of lim_sub and lim_inf also exist, but they are a little more rigorous on the mathematical side. So for now, we'll not go into that depth. Let us try to draw a parallel yet again from what we learned in school and what's the reality. We learned that probability of any set A or any event A is equals to m by n, that is the favorable outcomes divided by total outcomes. But how is this true? Even though what we learned that P of A is equals to m by n looks much simpler from what we used to do in these videos, that actually has a lot of assumptions that limit the complexity and rather introduce the concept only from the surface. So instead, here I'll tell you why this comes out to be the case. Suppose A to be x1, x2 till xm with m elements and omega to have n elements, let's say. So probability of A can be written as probability of union of all those xi's from I goes to 1 to m. Since these are disjoint elements, events, we can say that this is equals to the summation of probability of each xi from I to m, since all outcomes are disjoint. This turns out to be summation of 1 by n, which is equals to m by n. And this is a big assumption right here. How did we write P of xi to be 1 by n? Here we are assuming that all xi's from I goes to 1 to n are equally likely. That is why we take the probability of each event to be 1 by n, so that for all the elements together it constitutes to a whole probability of 1, because we know that P of omega is 1. And this is something that satisfies all the 3 axioms. You can check for yourself. Thus, we didn't care to define it rigorously back then. However, it is important to realize that the condition of equal likeliness is not valid in all cases, and thus a stricter definition of probability is needed. To sum it all up, we learned what probability is, its mathematical definition, some of its axioms and properties, and how it relates back to what we learned in school, which is a much simpler version of the intriguing subjects like probability. The deeper you go, the more you realize that. Hope this video added some knowledge and value to your foundational understanding of probability. In the next video, we'll go on to understand what conditional probability is and try to unravel some of the big assumptions that we create while reading the concepts in its simplest form. If you like the content, please don't forget to like the video and subscribe to the channel. Till then, stay healthy. Rachit Jain signing off.